So it's a pleasure to have Chrysoula Markou from Max Planck Institute in München, who will tell us about extracting bigravity from string amplitudes. Please, Chrysoula.
Thanks, Guillaume, and thanks, Marius, also for giving me the chance to present this work here at Planck Institute with Rencontres théoriciennes. So I will speak about a project that I initiated and led and worked on together with Dieter Lust, Stefan Stiepeger, with whom I suppose everybody knows, and also Puri Amaslumi, the PhD student of Stefan Stiepeger. So the plan is basically a trip from field theory to string theory and back. We're going to start with the ghost-free bimetric theory we're going to deal with and explain its basic properties, how we should compare if it comes to string amplitudes. Then we will move on to string amplitudes calculations. And then from them, we're going to extract effective actions and compare them with a field theory prediction from bimetric. So let's start with something very, very basic, and that is GR. How do we think of gravity? We think of gravity as a metric theory, and that's exactly how Einstein approached and formulated his theory of general relativity. Now, due to many authors, there is an alternative approach in the sense that it can be thought of that GR is the unique theory that describes the kinematics of a massless helicity 2 tensor. And to see this, you can do this very, very simple example. Just take a tensor, an h-mu tensor, and write all possible Lorentz invariant and local terms you can, and then impose that these terms are ghost-free. They don't propagate ghost degrees of freedom, but only healthy ones. If one imposes these assumptions, then what one gets is diffeomorphism, linearized diffeomorphism invariance. Sorry? I heard someone speak. Is it a question or?
I think that's a mistake. Let me mute the people who are not.
Sure, no problem. So what one gets with these assumptions is linearized diffeomorphisms. And in fact, it can be shown that you can promote these and the equivalent actions, full nonlinear diffeomorphisms, and general coordinate invariance that is, and as an action find the Ricci scalar, the Einstein-Hilbert action of GR. Now, from the string theory perspective, what Schecker and Schwarz first proposed was to identify a massless state that exists in closed string spectra with the graviton. And in particular, they considered this build of the bosonic transverse oscillators in the case of the bosonic string, this state, at the massless level of the closed bosonic string, which contains different representations of the Lorentz group, and in particular, the symmetric and traceless one corresponds to the metric. But this matching of degrees of freedom, which is how they initially argued, is not sufficient to say that one gets GR out of this. One has to compute and extract from string amplitudes the interactions of this G mu. And this is what was done later by Green, Schwarz-Brink, and Gross and Sloan. In particular, they computed 3- and 4-point amplitudes involving these fields at the massless level of the closed bosonic string. And from those, extracted at the equivalent order the Lagrangian, and involving symmetry arguments, derived the full low energy, so to speak, supergravity Lagrangian from that we all very well know. Now, let's go to extensions of general relativity. Let's consider in particular ghost-free bimetric theory, and I'll get to why in a bit. What is ghost-free bimetric theory? It is a theory of two dynamical metrics, each of which is described by an Einstein-Hilbert term. And they have their own corresponding Planck masses. So initially you start with two separate diffeomorphism invariances associated to these two metrics. Further, this theory involves a potential with no derivatives that is built out of the so-called elementary symmetric polynomials, En, here, whose argument is the square root matrix S. The square root matrix is built out of the inverse G times F, where G and F are the initial metrics. And this particular potential breaks the two copies of the diffeomorphisms to their diagonal subgroup, but in such a way that there is no ghost propagating. All the degrees of freedom that propagate with this potential are healthy. What you further see here is the parameters mg and mf, so the Planck scales, and also the parameters beta n that are here dimensionless, which introduce a further scale multiplied with a mass scale in front. So that is the scale, the interaction scale of the potential that can be tuned by the parameters beta and n, which can be arbitrarily large or small, in principle at least. Now, where was this potential inspired from? It was from ghost-free massive gravity, and in particular, DRGT, Deram-Kappa-Tolly, managed to find a way to promote the Fritz-Pauli mass term that Fritz-Pauli had written decades ago for a massive spin-2 field in Minkowski spacetime around the Minkowski background. They managed to do it for the full nonlinear theory. So they wrote a theory where there is an Einstein-Hilbert term for one action, and there is further a potential depending on this matrix, the elementary symmetric polynomials of this matrix, where you find an arbitrary reference metric. Now, it's because of this structure that they also avoid the so-called Bulwer desert ghost that plagues typically all other extensions of the Fritz-Pauli mass term around other backgrounds. And what Hassan and Rosen did was to promote this reference metric to a dynamical one. And that's how you get ghost-free biometric theory. Now, as far as the degrees of freedom are concerned, to count them and to see whether they're healthy or not, you need to look at the Lagrangian. You need to calculate the Hamiltonian. You need to look at the Hamiltonian, calculate the constraints, and count the degrees of freedom that are propagating. And those are 7 in this case. So in ghost-free massive gravity, there are 5 and healthy ones. In biometric theory, there are 7 and healthy ones, no Bulwer desert ghost propagating. Now, around general backgrounds, these 7 do not necessarily split, cannot be thought necessarily as of splitting into those of a massless spin-2, helistic 2 and a massive spin-2 field. But around specific backgrounds, this can be possible. So let's see what can happen. Before we actually go back to what can happen with the backgrounds, let's see exactly what I'm going to speak about today. So when I joined the Max Planck Institute as a member of Agnes Schmidt-Meyer's group on biometric theory, ghost-free biometric theory, I tried to sit and think what kind of concrete prediction we can make about this potential V that appears in the ghost-free biometric action from string theory. And one of the tools that one can use that gives concrete predictions are scattering amplitudes. Those are the observables. Those can tell you a lot about the theory. But in fact, it turns out that to determine the whole potential from amplitudes is not, it's a very ambitious goal, so to speak. And one should take several steps before even considering the full potential. How is that? It is because we need to treat the field theory perturbatively. We need to expand it around the background, because that's what we're doing in the string theory side as well. We're computing amplitudes who have specific points of external legs, and we're comparing Lagrangians in the end. So we cannot, in principle at least, in this setup using on-shell string scattering amplitudes, compare the full biometric theory. So the first step is to expand. The second step is to identify what fields we have in the field theory side with appropriate string states in the string theory side. And that is a choice. If one makes this choice, one can further compute amplitudes. But there is this constraint that one can only compute, at least to the best of my knowledge, on-shell amplitudes, which means that the external legs, which in our case are string states thought of as asymptotic states, they satisfy on-shell conditions. So this can only take us this far. This can only give us on-shell Lagrangians and vertices and interaction terms. So the next step would be to calculate these, the string theory amplitudes that we will consider. And from those, appropriately extract the effective action and compare it to the biometric theory with the hope of getting information on the potential. And it turns out that the first non-trivial case, in the field theory side of vertices, are cubic interactions. So we're going to consider 3-point string amplitudes. So let's start with the expansion, the first step, the very first step. This has been done before by other authors. And in particular, what we considered was this particular well-known solution of proportional backgrounds, where the two metrics are expanded for our particular case around Minkowski spacetime. And then at the quadratic level, it turns out that there are two mass eigenstates. One is massless, and here's this kinetic term here, where E theta, E calligraphic, is the Lichnerowitz operator. And this is precisely the linearized around Minkowski spacetime Ricci scalar. And so this state is massless, propagates precisely like the graviton does around Minkowski spacetime. And let's turn now to the other state, the massive spin 2 state. It turns out that its action is this one, nothing other, as expected, than the Fritz-Pauli action, because that's the only ghost-free action around Minkowski spacetime. So we have two modes. Their kinetic terms are both of the linearized Ricci form. And there is also a mass term of the Fritz-Pauli type for the massive spin 2 field. And you see here that the Fritz-Pauli mass is determined by the particular coefficients and parameters that enter the bimetric potential and in general the bimetric action. So you see here alpha, the ratio of Planck masses for the two metrics. Mg is the Planck mass of one of the two metrics. And you also see some of the parameters that enter the bimetric potential, the beta n dimensionless parameters. Now, this massive mode, this massive spin 2 mode, has been argued to be, based on its interactions with matter, one has to consider matter couplings to see this, a viable dark matter candidate. And so, ghost-free bimetric theory, if one compares it, for example, to ghost-free massive gravity, is interesting not only because it contains a massless graviton that at least perturbatively can be thought of as that of GR, but also because it contains the massive spin 2 that may account for dark matter. What these authors that suggested this for the particular case of ghost bimetric theory did was to expand further to cubic order the whole ghost-free bimetric action around proportional backgrounds. So here I give you, for example, the interaction terms between one massless graviton and two massive spin 2 fields. And what you see here are several terms. In principle, these are the terms we want to reproduce from the string. You see the first line, non-derivative terms. In the rest of the lines, two derivative interactions that involve always one massive helicity 2 and two massive spin 2 particles. And you see also that the non-derivative terms depend on the parameters of the bimetric potential, the dimensionless beta n parameters. Now,
sorry, Chrysoula, can I ask a question?
Of course, please.
In string theory, you can only get the on-shell interactions and action, etc. Whereas here you are expanding the off-shell theory. So the question is, there may be many off-shell theories, of course, that give the same off-shell action. So do you know what goes with which?
Very good. So I will show you in the next slides how we actually reduce ourselves to only the on-shell part of these interactions. And these are the only kinds of vertices we can reproduce from this string. Now, if you get the on-shell action, then you can perform field redefinitions to that and get off-shell descriptions of the Lagrangian. But those are not unique, and those cannot be determined from the string. The string doesn't know about these, so to speak. All right. So let's summarize what these authors see at the cubic level for the two modes. For G, the graviton, they see that there is no term that doesn't involve derivatives. And the only two derivative terms that appear are those that one obtains from the linearized Ricci around Minkowski. So even at cubic level, this is the graviton in ghost-free biometric theory around Minkowski backgrounds.
Sorry, again, I'm confused. So what are you describing here? What comes out of string theory or from which theory?
All this now is field theory.
But which theory are you using to say there is or there isn't, etc.?
So excuse me, the what?
What is your original gravitational theory?
Ghost-free biometric theory expanded to cubic order around Minkowski backgrounds.
But there are millions of such theories. Which one?
We use precisely this one here. And the arbitrariness I suppose you refer to has to do with the coefficients. But the structure here is very well determined.
Okay,
if you don't use the elementary symmetric polynomials and the square roots, you get something that propagates unhealthy degrees of freedom. For example, the Bulwer-Tesler coast.
Okay, thank you.
Of course, no problem. Okay, so moving on. G cube is the graviton at cubic level. Let's move on to M cube, to M, the massive spin 2. This one has terms that don't contain derivatives, but it also has two derivative self-interactions. And those are again of the Ricci, linearized Ricci type. So what we see is that G cube and M cube at cubic level, at cubic order, have the exact same kinetic structure, and that comes from the Ricci. M further has an M cube interaction, like a trace and combinations of traces. So trace M times trace of M squared and so on, at least off shell. And there are further interactions that involve G and M and two M's. And those are both, as I said and showed to you in the previous slide, of the non-derivative type and of the two derivative type. What is important to say is that there is no term that involves one massive spin 2 and two massless spin 2. So there is, as the authors explain, there is no chance that this massive spin 2 can decay in massless gravitons. And what you also see as a last note is that all the couplings depend in a non-trivial manner, the couplings of the vertices, on the parameters of the biometric action. So the two Planck scales and the beta n coefficients, dimensionless coefficients that enter the biometric potential. All right, so as Elias very well pointed out, we need to consider on-shell conditions. Why is that? In string theory, one calculates string amplitudes by considering states, putting them on the external legs of the amplitude, and using the respective vertex operators who satisfy on-shell conditions because of BRST in the case of the string. And those on-shell conditions are of what type? First, they contain the condition that the mass is on-shell. So the massless graviton should be m squared equals 0, and the massive one should have a mass proportional to the string scale, or like to the square root of the string scale. And they should further be transverse and traceless. So these two constraints that come from the string, we need to impose on the field theory side. And how do we understand this field theoretically? In the following way, we take the Lichnerowitz operator for the action basically for the spin 2 and the massless one and the massive one at the quadratic level, and bring it to the form of the Klein-Gordon equation. For the massless graviton, this means that as gauge choices, transversality and tracelessness are further imposed, which reduce the number of propagating degrees of freedom to 2. In the case of the massive spin 2, however, the Klein-Gordon equation is that of the massive form, and there are further the transversality and tracelessness constraints, in this case, not gauge choices because there's no gauge invariance, which in the end reduce the number of propagating degrees of freedom to 5. So here you see explicitly the split around Minkowski spacetime of the 7 initial degrees of freedom to 2 and 5. And these conditions now we will impose to the ghost-free bimetric action as expanded to cubic order. And what we get is much, much simpler expressions here after lots of massaging of the Lagrangian and partial integrations. So let's sit and look at this. We get g cube, gm square, m cube. By the way, the fact that the g cube interactions and in general self-interactions of G of the graviton are only of the Einstein type, of the Einstein-Hilbert type, is a well-known theorem by Henot and and Boulanger and collaborators. And this is also confirmed in the case, of course, as it should, of biometric theory. So here you see these three kinds of interaction vertices. And you see that the only case in which the beta parameters of potential enter are in the case of the M cube self interactions. Before we go on shell, we had them appear also in the case of GM square interactions, but not here, not on shell. So let's see exactly what these terms are. We see that only a term of the kind M cube trace, whatever you see brackets, it means trace. Trace of M cube survives, but the trace of GM square, a non-derivative interaction of the massless and the massive spin 2 disappears on shell. But if you look again back, let's go one step back for the GM square, what you see is that these are all possible Lorentz invariant terms that one can write for transverse and traceless fields up to partial integrations, of course, that are of rank 2, massless and massive. And finally, you see, based on further considerations of the cosmological constant that we also explain in the paper, that there are 4 free parameters in this case. So let's go back. You see only beta 1 and beta 3, which, if you remember, initially in the potential are 5 in total. And then you see alpha, the ratio of Planck masses, and mg, the Planck mass of one of the 2 metrics. So if one disregards the way the couplings depend on the ghost-free bimetric theory parameters, the particular structure of the terms is not unique to ghost-free bimetric theory. You see this? So if we go back, in principle, this could come, this GM square interaction can come from anything, not necessarily this ghost-free bimetric theory. We have lost information, inevitably. Anyways, since the particular couplings do depend, and since we don't know exactly what the string will give because nobody calculated this kind of amplitude before, we will turn to the string computation. And first, we need to identify the states that we were going to use in the spectrum. So we're basically looking for 2 fields. One that is the graviton, which we very well know how to identify in the critical dimension of both the bosonic and the superstring. And further, we're looking for a massive state that propagates the degrees of freedom that correspond to a massive rank 2 tensor in the given dimension. And these are 5 and 4 dimensions, as we saw, 44 and 324 in the critical dimension of the superstring and the bosonic string, respectively. So now we look in the spectrum, really. We scan the spectrum for this kind of state. And notice that it's not a sufficient criterion for the number of the degrees of freedom to be such. It further has to be a rank 2 tensor. So it's not sufficient, it's 44. It could be something else that dynamically propagates only 44. We need to look at rank 2 tensors. And then the question raises itself in a sort of existential manner, if I may say, as to whether this state is a closed or an open string state. And in fact, Dita, with collaborators, Alex Quejas and Sergio Ferrara, they considered the particular case in which Weyl square supergravity may have a realization in regard to open strings, so that the massive mode, the massive spin 2 that appears on the open string spectrum, on the open string tower, may be naturally thought of as the massive mode that appears in Weyl square supergravity, which, by the way, is a ghost there. Anyway, based on this drawing motivation from this work, we first choose to identify the massive spin 2 with an open string state. And what does this mean? From the strings side, all masses depend on alpha prime on the string scale. And in particular, they follow regular trajectories. So if we make this identification, and we'll show you in the next slide exactly what the state is that we use, we are forced to assume, at least for now, that the Fitz-Pauli mass in the field theory side is equal to the mass of the state from the string. So we get this relation, at least in principle, between the biometric parameters and the string scale. Now, in what is not part of the present work or present paper that I'm presenting, are further possibilities, namely in cases in which this massive spin 2 may come from the closed string spectrum even. But let's remain on the open string. So what I'm telling you, and this table you can find, it's by now text material, is that we're gonna, of course, deal with the graviton as everybody does in the closed string. But for the massive spin 2, we're gonna consider here in the superstring case, these particular states at the first massive level of the superstring that build up a massive spin 2 field state and an anti-symmetric rank 3 tensor. So what you see here is that the bosonic and fermionic oscillators at this mass level with m squared equals 1 over alpha prime, the first massive spin 2 that you encounter, they build up this massive spin 2 and another anti-symmetric tensor. And what is instructive to see here is, let's think of these indices as being the transverse indices in 4 dimensions, just for a sec, just to understand what's happening. Remember the massive spin 2 has 5 helicity states, so +2, +-2, +-1, and 0. So we need to account for these using these states. And in fact, it turns out that from here, we build part of it, and from here, we build a further part of it. So a combination of these two results in the massive spin 2 little group representation that we consider. It's almost time to consider, to start calculating amplitudes, but we're not ready yet. And why is that? Because—
sorry, Chrysoula, are you using light cone notation?
Precisely, so that's why I said transfers before.
So then you will do the computations in the light cone formalism?
Yes, but we're going to use vertex operators. And so there the index mu is the spacetime index. Right, I'm going to show exactly what we use in a bit. Let me get there in a bit. Right, so let's first consider a generic expression, the generic expression for an amplitude that describes at tree level the simplest case of scattering between involving closed and open string states, and that is an amplitude on the disk. Here is the most general expression. And what is exactly this expression? It is actually the correlation function of vertex operators that correspond to the string states that we put on the external legs of the amplitude. And you need to evaluate on the worldsheet these correlation functions. And that's why we get the integrals. You need to integrate over all possible insertions of the vertex operators on the disk. I'll get to that in a bit, exactly what that means. So we have the master formula, and in particular, specific cases had already been considered before by Klebanov, Hashimoto, and collaborators, in which the scattering of massless states, or massless closed strings from the brains, which we're gonna see is also related to our case, was considered. Now further, Feng, Lust, Schlotter, Stiebeck, and Taylor considered the case of scattering of one massive open string state and other massless states, but nobody had ever considered before the case of the external legs being at all spin 2, and at least 2 of them being massive. And these two novelties that we do significantly complicate both the calculations and also the derivation, the extraction of effective actions. So let's see first what kind of vertex operators we're going to use. So here you see the well-known vertex operator for the graviton from the closed string. And what you see is that it is a conformal field that depends on the worldsheet coordinates on the disk, inside the disk, because it is a closed string state. And also it depends on the polarization and momentum that this state is thought of as having. So the vertex operator is built out of the coordinates x mu, the string coordinates, the embedded coordinates x mu and psi mu. It's a superstring, so they're fermionic and bosonic and fermionic too. And it has to satisfy, because of BRST, these particular conditions that we mentioned before, the on-shell conditions, which are basically what I showed you before from the field theory side, but here written in momentum space. You see, this is just transversality, this is masslessness, this is the symmetric, the fact that it's a symmetric representation of the left group, and this is tracelessness. So we get precisely the same conditions. Let me put it otherwise, actually. We know that these come from the string and we have to impose them, as I said before, on the field theory side as well. Now, these vertex operators are always written in a superstring in a picture, so to speak. Because of superconformal invariance, there are many ways that you can write a vertex operator for a specific state. So the state is unique, but the vertex operator is not. And the amplitude is, because it's an observable, so the way that this ghost, the ghost picture is sort of, the ghost charge is distributed along the vertex operators within an amplitude, is in fact meaningless. So you can choose it arbitrarily. But it should be in such a way that you cancel the background ghost charge of the disk. And that's why we need vertex operators in several pictures, depending on what we want to calculate what the external states are. Now, as far as this massive state that I showed, that we identify the M, the massive spin 2 width, is concerned, the vertex operator, the vertex operators were built here. So can you see the bottom of them? Because I cannot, of the page, Guillaume.
Yeah, we see everything.
Okay, perfect, perfect. So in these references, they were constructed, the vertex operators for this particular state. And again, they have to satisfy the on-shell conditions, much like the graviton has to, the graviton vertex operator has to. And again, these are the very same ones for the massive spin 2 that we saw in the field theory side. But notice a difference. So in the field theory side, for the graviton and the massive spin 2, transversality and tracelessness are gauge choices and constraints, respectively. But from the string side, they're both due to BRST. So qualitatively, very different origin. Now, as we're going to see, we're going to need this vertex operator in two different pictures. So this describes the very same state, but in some degeneracy, so to speak, for people that don't work in the amplitudes.
May I ask you something?
Of course, please.
As far as I see in your open string vertex operator, you also have a color associated to those massive gravitons. So I guess you have several of them. So how does it fit then with double metric gravity, bigravity, since you seem to have a multi?
Well, look, by gravity, you can write it without the gauge group. You don't have to couple it. And that's exactly what we consider. We don't consider matter couplings or couplings to gauge fields until now. But anyways, we will see that in the amplitudes we can consider, this trace, the gauge group, is going to appear as a prefactor of as is typical for this kind of amplitude.
I see that if you compute just a 3-point amplitude in this way, it's just the same as if there was no color. But if you are computing all order, yeah.
Let me explain. It will appear, but as a trace of a product of generators, as we will see. And this we can argue that you can ignore, at least for our purposes.
Why you can ignore it? In fact, we know that this theory is inconsistent if you ignore it, right?
well, we were going to deal with another inconsistency. So, okay, let's get there, and we're going to see whether it makes sense to ignore it or not. Let's get there. Let's
yeah. So go ahead, please.
Yeah. No, just let me bring some water, please. All right. So now we're ready to evaluate the amplitude that has as external states 2 massive spin-2 fields and 1 graviton, the ones we have identified. So for that particular case, you have only these kinds of integrations because you only need to integrate around the boundary twice for the 2 open string states. And also you need to integrate over the disk because of the closed string states. And what you see here is precisely the correlation function of the three vertex operators I mentioned. And we choose them in such a way that the total background charge of the disk is canceled. But we can make another choice. This is not a unique choice here that we make, that it's -1, -1, 0,0. The point is that no matter which picture you choose for the particular vertex operator, so long as respect that the totality cancels the background charge, the observable is the same. And we're going to compute this correlation function, which is actually a very laborious task, on the disk. That's exactly what we said that this amplitude is in the most simple case. And so we need to use correlators of the x mu and psi mu on the disk. Now, what is the scattering exactly? It's as if you have a brain and it's a fixed target experiment and you throw at it closed string states in an elastic manner. And because it's super heavy, the brain, momentum conservation only makes sense to consider along the brain. So in fact, this is reminiscent, if you want, of how experiments at CERN are treated, in the sense that only on the transverse plane it makes sense, of course, for very different reasons, to consider momentum conservation when it comes to protein-protein collisions, because of the PDF functions for this. And there, actually, a good observable, a good signature of new physics is the transverse or missing energy. Anyways, momentum conservation along the brain takes this form. So here, remember what we said, with K, you will always see open string states. And with Q, you will see the closed string state momentum. So what you see here is this momentum conservation along the brain, because K1 and K2 are, by definition, thought of as being along the brain. If it's an open string state on the brain, it has momentum along the brain. And then you need to consider that part of the closed string momentum that is along the brain. Now, there is a way to split, to write them parallel and transfer to the brain momentum of the closed string using this D matrix. This D matrix is related to the boundary conditions that your embedding coordinates have to satisfy, can satisfy, because of the boundary that we have, because we have closed strings interacting with open strings, because there is the brain. And because of this, actually, you can treat Q and DQ as 2 different momenta, K3 and K4. So K1, K2, the open string momenta, and K3, K4 correspond to the closed string. And in some zips, you can even define Mandelson channels, so the STU variables this way. It's a 3-point amplitude, but it involves closed string in the boundary. And so you can treat it, at least kinematically, and also, in fact, inside the correlation functions, as a 4-point amplitude. Okay. If you do some manipulation using the momentum conservation of the STU Mandelson, what you can find is that there exists only one kinematic invariant in this case, so the rest are redundant. And let us choose, for example, S. You see here that S is a constant times alpha prime times momentum. And this constant here is precisely because we consider massive states. If the external legs were all massless, this constant wouldn't be there. And this complicates the truncation to the effective action a lot, as we'll see. All right. So what do we do pragmatically? How do you calculate it? You substitute here for the vertex operators using the expressions I showed you before that involve x mu and psi mu. And then you start using extensively Wick's theorem and all the correlators on the disk that involve the two kinds of fields. And those correlators also involve the D matrix that depends on the boundary. And you perform these computations, and you also need to fix the PSL2 invariance of the disk. And there's a prescription to do that. Let me not get too technical, or we can discuss it, of course, if you want, but I'm trying to be as pedagogical as possible here. And what you get is this amplitude here. So this is not generic, it's just the way that we chose to organize our terms after having performed all the contractions and inserted and treated the conformal Killing group volume, the infinity of that. And in particular, we organize the terms into 4 packages, 4 groups of terms, so to speak, depending on the power in which x1 minus x2, x1 and x2 are the positions of the 2 open string vertex operators that appear in the denominator. So A4, for example, it comes after, it contains all the terms after the contractions that we have performed that have come up with 1 over x1 minus x2 to the 4th. And we get an A3, an A2, and A1. And you see these are very many terms. And now the integral we have to do is just over the real line because we have fixed PSL2R. And what you see here is that in every group of terms, we get many integrals, and to each integral corresponds a different kinematic package. For example, let's look at A with 4 indices. What is A? It comes from the numerators of the contractions, and it involves Q and DQ. So basically, NK1 and K2, the momenta, all the momenta of the 3 external states. And then of course it involves the matrix D, the boundary contribution. Now, what is important to remember is that all these kinematic packages that we compute, we have computed all of them, which are 36, as I show in the next slide. They're very long expressions and quite tedious to obtain. All of them are exact expressions, exact polynomials of alpha prime. They're not expansions. We have not truncated in any sense. It's just that they contain different terms that correspond to different powers of alpha prime. Now, all of these contain minimum alpha prime and maximum alpha prime to the cube order. And here I just give you the simplest one, just to give you an idea, and the rest you can say in the paper of how things work. We're not yet truncating because we have to do the integral. So let's move on. To do the integral, we need to do partial fraction first, massage again the expressions we have found, such that different kinematic packages combine, and then we evaluate the integrals appropriately. We're using a trick, and get products and fractions of gamma functions. And as you see, for example, here, we have contracted with the polarization tensors of the external states, and now this E contains contributions from 2 different kinematic packages we had before. So schematically, if you don't want to see all the formulas, what happens is we have an amplitude that is written as a sum of terms AI, whose structure is the following. It's kinematic packages that depend on momenta and alpha prime, and the polarization tensor, of course, times an object that contains contributions from the integrals that we have evaluated, and also from the Kobanilse factor. So it contains a prefactor of 4 to the S. I can explain what it is in the end if you'd like. But anyways, these objects are infinite expansions in S. So as I said, the case, they contain specific terms in alpha prime, not up to an order because of a truncation, but just because that's how the correlation function is. But the integrals, they have an S dependence in a rather obscure manner that is hidden inside the arguments of the gamma function and in the prefactor 4 to the s. Now, we have computed the full amplitude that corresponds to this scaling process, so to all of these kinds of terms. And this is valid in the critical dimension, but also it is valid in 4D because the vertex operators we use, no matter which compactification you make use of, they remain the same. So this amplitude is exactly equally well valid in 4 dimensions. And also, because we kept the D matrix arbitrary, it's valid for any D brane, any dimension of the D brane you want to choose. All right, maybe let's think a bit more about this before I move on to the next slide. And that is how we're gonna get the effective action, right? Normally for massless states, what people do, what Gross and Sloan did for the case of the graviton, was to consider a small alpha prime, right? That's exactly what happens. We want to do here the same, but the dependence on alpha prime of these objects I and of S is obscure. We need to analyze it. Can we really just expand this object here that comes from the integrals for a small s, for a small Mandelton? It turns out it's much more complicated than that because of the massive states. So let's look at these objects for a bit. Remember K1, K2 are the open string momenta, and Q is the closed string momentum. And these objects enter the Mandelstam, both of these. Now, for small alpha prime, naively, if you forget that these are massive, you think that this whole object goes to 0. But this is not true because K1 square and K2 square go like 1 over alpha prime. So the whole object for small alpha prime approaches 1 in particular. It becomes of order 1. In contrast to alpha prime K1 or K2 times Q, where Q is now the closed string, which is massless, which indeed approaches 0. So if you look now at S, and this is the single kinematic variable I showed to you before in the previous slides, for small alpha prime, this object here goes to 1, and so the combination of these two goes to 0. So at least we know which value of S we want to expand around. It's around 0 and not around -2, for which would be the naive case for massless states. However, let's expand. Let's say we expand in small s and then substitute S via this relation. What we want to do is extract the effective action, which means we want to truncate once we substitute the polarization tensors with fields. And so if we do this truncation, what we will get is a series in this, which is not, it's a dangerous object. It becomes of order 1 as alpha prime goes to 0. So the truncation, if one uses this parameterization of S, it loses meaning. We need to choose something else. And so what we did was to just use the momentum conservation here and write S as a kinematic invariant depending on K1 and Q, with Q being the closed string momentum. And using this, we plugged back into these objects that multiply the kinematic packages, and then we expanded for small s. And so what we did was to obtain in the end the amplitude for small alpha prime and small s, but not set to 0, neither of the two. And now this up to order alpha prime square, and in fact up to momentum square, k square and q square order. So this is the amplitude, that we get after this meaningful truncation. From this, now we're able, we have, oh, by the way, we have set d equals to g, to delta actually. So d mu nu with both the indices up is g mu nu with both indices up. And from this now we can extract the effective action just by mapping K1 and K2 to partial derivatives that we have to make sure they act on the respective fields. So K1 mu should act on alpha 1. And also we replace the polarization vectors with the fields. So this is basically the replacement we do as a standard. And from this, what we obtain is this effective action. So you see here in front, the string couplings, and of course the alpha prime, the string scale. And inside, what you see is only two derivative terms. So let's compare with the bimetric prediction at cubic level. It is this action. So just upon comparing the two, what you see is that all the coefficients are the same. Not only have we derived the exact same Lorentz structure of terms, but also the exact same coefficients. Upon setting, of course, that the full the coupling in front of these kinds of vertices match the string, from the string, the one to the field theory. But still, we do not know if this is meaningful. We need to look at other amplitudes as well. And also, it doesn't give any information on the beta parameters in the bimetric potential. It just tells you something obscure about the Planck masses in the case of the biometric theory. So because of this, we then turn to M cube. What is M cube? It is the amplitude that involves in the external legs 3 massive spin 2 states. And in this case, again, it's a disk amplitude that involves, that is a correlation function that we need to evaluate of 3 massive spin 2 vertex operators. So now you see that to maintain a ghost charge of -2, we need to use the same state in different vertex operators. And now the kinematics is simpler. You take this form. And also, after treating the conformal volume, what you see is that there's just one integral, but in fact, the x dependence of it goes away. And so there's no integral to perform in the end. And so the procedure to extract the Lagrangian is much simpler. So let's see what the amplitude is that we obtain. It takes this form. Now note, this is the full amplitude. It's not differentiation. This is precisely what the string gives you. We have not expanded around alpha prime or S or whatever. Okay, there's no S here because it's just the massive spin 2 3-point amplitude. So it contains terms with no derivatives, with no momenta in this particular, in this description, because it's the amplitude, not the Lagrangian. It contains in the second 2 lines terms with 2 momenta, and in the final 2 lines, terms with 4 momenta. So now, before we extract the Lagrangian, we see a problem. Let's compare with the graviton amplitude. The 3 graviton amplitude, it can be calculated on the sphere, or if you have a boundary on the disk, and there's many people that have calculated that. And it's universal. It has the same expression, at least the 2, if I remember correctly, the 2 derivative terms for all these kinds of cases. And what is that? It's just these 2 lines, the 2 derivative lines, the 2 momenta lines, second and third here, but with a different coefficient in front of these terms. So the 3 that I have in orange here, that comes from the string calculation of massive spin 2 states, is not there in the case of the graviton. The graviton 3-point amplitude is not the same, okay? But remember, we said, I showed to you that from the bimetric point of view, G and M have the same kind of derivative interactions at cubic order. And those are both of the kind of the Ricci, linearized Ricci type. Okay, so if we want to match, if we want to have any hope of matching, the amplitude should be exactly the same, at least in regard to the 2 momenta terms, and they're not. So we already have enough evidence that we're not going to get a match.
Sorry, Chrysoula,
yes.
Why do you get terms with 1 derivative?
Where do you see that? No.
Sorry, there are 2 derivatives. Sorry.
Yes.
Yes,
so
yes.
No problem. So no momenta here. The first term is the no momenta.
No, it's okay. Sorry, I didn't.
Okay, no problem. And actually, by the way, this no momentum term is because we have a massive state. So that's why it doesn't appear in the case of the graviton. All right, when we first saw this, actually we calculated the Lagrange, and we'll come to that in the next slide. But what we also did was to check if the bosonic case gave the same result as the field theory side or not. And we did the same calculation for the case of the bosonic string. So we identified the mass of string 2 with a bosonic open string state. And again, there is no match of the amplitude. So in fact, we get a 4 instead of a 3 here. So let's see what the effective actions are. What we get from the M cube is this, after doing the replacement of the polarization tensors and derivatives, as I explained. So let's compare with the prediction from the bimetric, from the ghost-free bimetric theory. You see the M cube term with no derivatives. You see the 2 derivative terms, and you see the 4 derivative term that now in our case is something like a string correction. But you see explicitly that the coefficients do not match. Now, this coefficient, now it's more clear. It should be uniquely 2, so as is the case of the M cube from ghost-free bimetric theory, if it comes from a linearized Ricci. This tells us that the M cube, the massive open string state that we considered, does not have kinetic terms at the cubic level of the Einstein-Hilbert type. Okay, so this breaks at this level linearized diffeos, so to speak.
Sorry, Chrysoula, let me ask a question going back now to the original theory. You chose a specific theory which is ad hoc, right? Because as we know, the massive part of the theory could be many other things. So why do you find this surprising? I would have expected first that you try to write what's the most general quadratic term and the most general cubic term you could write in that theory, which is compatible with all the invariances you want, etc. And then compare with the string and see whether you get all of it or you get part of it, etc. Right?
Right, but we want to do it in a ghost-free manner. So if you—
What do you mean by ghost-free manner? Around flat space, ghost freedom is simple, right? You mean that in that particular theory at quadratic and cubic level, you cannot write other terms that don't give you ghosts beyond some cutoff?
At the quadratic, I think there's no other term, right? What else can you write? There's nothing else.
Why there's nothing else?
No, for on-shell. If you want on-shell fields, then you're very restricted, right? That's what I'm saying. I mean, these terms are not really— I see what you mean. They're not really the terms that unique, though, to ghost-free bimetric theory.
But then let's go to cubic. What about cubic? What are the most general cubic terms you can write that are okay?
I think these. So Lorentz invariants, only Lorentz invariants. And for the case of the graviton, they should respect something like linearized diffeos at this level.
Right.
But for the massive spin 2, they also should, if you look at it from the field theory side. That's what the adjectives do. That's what—
No, but you have a single diff invariance, not 2. I mean, this analysis—
yes. True. Wait, of course. But the thing is, this massive spin 2 that people like in the adjective treat or in Fitz-Pauli, they always assume that the kinetic term is that.
But this is, in your case, it's clearly wrong because these are adjoint gravitons, as Guillaume very well pointed out before, right. And therefore you cannot have a Ricci tensor for this.
Why is it because of the adjoint though? Because that comes as a prefactor. Why does the prefactor—
It comes as a prefactor order by order in the expansion, but if you try to package it in the single tensor—
that is true. That is true. No, I understand what you mean. But you see, it's here at least, it's a common prefactor. So it doesn't disturb the relative. It disturbs what you're saying, order if one compares order to different order, but not in the same order. You see what I'm saying? This is just cubic terms. So this relative, I don't think I expect.
Right, but they don't have to be the same as that you get by expanding the Ricci.
No. At this order, yes. because it's the gauge group is just a common prefactor. It's an overall.
I think it's good to have discussion, but we are close to the end of the talk of Chrysoula. So I think it's good if Chrysoula finish and then we start again the discussion.
Sure. Anyway, yeah. So anyways, because of this mismatch, what we see is that we cannot really try to figure out what the beta parameters are by comparing, because the coefficients will never match because of this 2 versus 3 discrepancy that we call. So as I said, this kinetic term is not of the linearized Ricci type, but remember that the brain we're using, because we went down to 4D, and again in 4D, we think of it as being space-time filling, it's not breaking Poincare invariance, just so you remember. Then again, on this brain, there is no massless spin 2. The massless mode is a vector mode. And so in some sense, what this is telling us is that from the massive spin 2 action we got, we can never get to a massless one. The kinetic part will never respect that of a healthy moving graviton. And because it's 2 versus 3, one cannot help but think of the Vedivisi, the Van Dam, Veltman, Zakharov discontinuity, in a particular manifestation of which there is an 1/2 versus 1/3 discrepancy. In what sense? One looks at the propagator of the graviton of the massive spin 2 and takes its massless limit. And what one sees is that up to singular terms, it takes the exact same form as that of the graviton, but the coefficient here in front of one of the terms is 1/3 instead of 1/2, that is the case of the graviton. And this particular discrepancy is because of the mass term of the massive spin 2, and it is a sign of the fact that the massive spin 2, even in the massless limit, propagates a different number of degrees of freedom as opposed to gravity, as opposed to the massless graviton. And so qualitatively speaking, this is a very different discrepancy compared to our own, which is at the level of the kinetic terms at cubic order. All right. Okay, so this brings me to the conclusions. We have the full amplitudes for 1 massless, 2 massive spin 2 states, and 3 massive spin 2 states. And those perhaps people will be interested to use for other applications, not restricted to 4D, not restricted to the brains being space-time in 4D, not restricted to effective actions. Now, what we see is that the massive spin 2 state that we use, to identify, does not seem to be a suitable candidate for the massive spin 2 mode of goes through biometric theory. And currently what we're investigating, what will be part of future work, is other options, namely closed strings and open strings, higher modes in the tower, for example. So this brings me to the end. Thank you very much.
Thank you, Chrysoula. So we can maybe unmute ourselves and thank Chrysoula for the nice talk.
Thank you.
So it's time for questions.
By the way, I have a question, Thibaut Damour.
Yes, please, Thibaut.
Yes. Are you aware of the works in 2000 of Buchbinder and colleagues, where they try to do this, but in a background field computation using the first massive state of the open string as a massive spin 2, and then they got a discrepancy, a mismatch at the cubic level for the GMM, for 2 massive and the Einstein background, where they got a coupling to curvature, which is different from the one in the Lichnerowitz operator and the usual massive bigravity. Are you aware of this?
I see. In the beginning, I thought you were referring to other papers by Buchbinder. This particular one, no. So I have to look at that. But it seems very similar then, if that's what you're saying. it was at the level of coefficients, the mismatch, or like whole terms were missing, you mean?
No, a whole term, like...
okay, that's different. That's, yeah.
Yes, and by the way, this is something we commented on in a recent paper with Vasilis and Nikiforova, where
I see.
Using a different thing which had been introduced by Sezgin and Juvenhuizen, which is a way to introduce a massive spin 2 by using Einstein-Cartan propagating torsion theories. Then you get actually something which has a different coupling to, I mean, the massive spin 2 is included in a propagating torsion, okay? But it has a different coupling to background gravity, the massless gravity, than the one of Hassan Rosen.
I see. And if I remember correctly, it's again 7 modes that propagate in torsion, right? Torsion gravity. The theories you have considered.
Yes, it's a good, so far as we know, no ball where there's a ghost. I mean, good number of degrees of freedom, but different to the background.
Right. Okay. Thanks for letting me know.
Yeah.
Yes, I'll have a look, of course. Absolutely.
Costas, please.
Yes, hi, Chrysoula. Thank you for the nice talk. I have a question and a comment, actually, related maybe to Elias. The question is quick. I guess you must have done also the Kaluza-Klein calculation of the corresponding thing, namely 2 Kaluza-Kleins and the massless graviton. Have you done this, and do you know the answer?
No. When you say Kaluza-Klein, you mean the compactified? What do you mean?
Yeah, just on a circle, and then
so field theory.
Do a Z2 orbifold so as to, or in string theory, and get rid of. You haven't done this?
No, we went straight for the string amplitude.
I think, Costa, this was done by Defayet and Robauts.
And do you know the answer? I mean,
I don't know the detailed answer, but I think they analyzed it. That's when they showed that in this case, the way that the Weinstein discontinuity disappears is because of the couplings to other gravitons.
You mean higher Kaluza-Klein modes?
Yes.
Yeah. Anyway, my question, I think it's related to Elias, is that in what you are doing, the underlying word identities are those of string field theory somehow. So BRST, invariance of string field theory. This doesn't have to be indeed the same as diffeos of by gravity. So could this not explain the discrepancy? Somehow it's word identities that should fix this coefficient.
Yes, so actually we thought of that, but not in the sense that we can explain it. We just confirm that the M cube amplitude does not satisfy the word. The diffeo word, I mean, the word that corresponds to linearized diffeomorphisms. But to actually argue that that's the reason, I don't know, that's a strong statement, right?
I mean, Sagnotti and others in the past have worked out order by order the word identities, the string theory word identities. Probably they relate you to higher spins, I don't know, but I would try to understand from there if you can understand your factor of 2 or 3, whatever.
Chrysoula, do you, in your original action, do you have more than just a single diffeomorphism invariance?
No, you have a single one, but...
But the word identities of string theory contain, in particular, this diffeomorphism invariance. So they contain more, certainly, as Costas is saying, but certainly they contain this diffeomorphism invariance, and therefore they impose these constraints and maybe more. That's why I asked, in fact, before, that I think a crucial question to be asked before going and doing the string calculation is to write your effective action at cubic order in the field theory, see what are the most general allowed terms modulo field definitions given the fact that you have a single diffeomorphism invariance, and then try to see whether you get all of them or part of them, etc. Because you start from a very special theory, which could or could not make sense. And then you're trying to compare, and then you see it doesn't match, but what have you learned?
I understand what you're saying. It's not a matter of taste that I'm using this theory. The reason is twofold. First, that it accommodates the graviton. A second, that there has been phenomenological research showing that, I mean, it's that paper by Agnes Schmid-May, Evgeny Babichev, and collaborators, 1,000 collaborators, where they show that the massive spin 2 with a mass less than 100 TeV can account for dark matter. So I have two very strong reasons.
Yes, but there is also a bias in people who deal only with gravity classically, that they think that anything that has spin 2, whether it's massive or massless, has to be described by a Ricci tensor or a Riemann tensor.
Sure, I can accept
absolutely,
that.
There's absolutely no reason for that.
I can accept what you're saying, which is why our amplitude computations stand on their own. You see, they can be a paper on their own. They don't have to be compared even with nobody ever.
Right, but I think it is an interesting exercise in view of your results to sit down and write, in fact, the most general cubic action of a massless plus a massive graviton given an overall diffeomorphism invariance.
I understand what you're saying.
And see how much more general things you get.
Yes, that's a very good point. So I understand what you're saying, but that would be more general in the sense that even in the naive massless limit of taking this, you wouldn't have two diffeos. I understand what you're saying, yes.
Right, yes.
That would be a great next project, absolutely.
One more question, by the way. There is a massive graviton, I think level 2 or level 3 in the closed string. Why don't take that one? What's wrong with that one?
Very good. So I'm actually, even if I may say, inclined to think that that might work. We have considered it. It's just it's going to be part of a next paper because it's much more complicated, the calculations. That's all.
So it's unique in that case? It comes as a single massive graviton, or are there several of them?
Unique in what sense? It's an infinite tower. You always have several copies of them. But in
well, there's
any
an infinite
level,
tower, but there are already trajectories.
Yes,
so
yes.
It's not necessarily
at any level, there's a single massive spin 2. Yes, absolutely. It's precisely as what I show here, but for the closed string, where is it? But for closed strings and for, you build in the exact same manner and you see that each level, I think there's a constraint on the highest spin. So it max, depending on which domain you are in, open and closed, bosonic and superstring, you can have a specific maximum spin states, depending on the respective mass level, but from one point and on, they always, or at least in many cases, contain massive spin 2 fields. But yeah, we never said that this is unique, you see. We can, even here, even in the open string, you can go to higher levels and consider the higher, like with mass 2 over alpha prime, massive spin 2. That is like in 1 or 2 levels from now. You can do that, but it's just, it adds to the technical complication. You have to find you have to start with a general vertex operator, impose BRST, see what the constraints, split the degrees of freedom in, find the vertex operator you want to use, do the calculation. It's several steps.
Oh, well, the closed string will be much more complicated. I can understand that.
I'm not sure.
Chrysoula, by the way, I think I mentioned before the paper by Defayet and Robautz. What they did is indeed they took a Kaluza-Klein graviton and Einstein in higher dimensions, and they looked how the tower of massive gravitons coupled to the massless graviton, you know, once you reduce in one dimension. Mm-hmm. And what they saw was interesting and, well, in retrospect, may be expected, that although the leading massive graviton has a Weinstein scale at which it becomes strongly coupled, etc., at the point where it starts getting strongly coupled and where you would expect something different to happen, the next a massive graviton comes in and cancels the contributions, and the whole thing sort of tumbles down all the way, so that instead of having various Weinstein scales in the theory, you still have one scale at which the theory breaks down, and this is the Kaluza-Klein scale, which is, of course, nice and in retrospect expected, but you can see it explicitly. Now, we suspect something like this happens also in string theory, although this was never checked. And I guess maybe with your results, you could probably check this among probably the first 2 states in the tower. Because in string theory also, if you calculate the associated Weinstein scales, that are much smaller than where you expect the theory to break down, which is the string scale. That is the effective action to break down, which is the string scale.
Yeah,
and it should happen precisely in the way it happens by the particular way all the various massive gravitons in the tower couple with each other and the massless graviton.
Mm-hmm. Yeah, I see what you mean. I have to look at this paper, but absolutely, it sounds like a great direction for the continuation. I don't exactly understand what you're saying by, so the next graviton comes, you mean, so you consider somehow the full tower in some sense?
Well, eventually, of course, in order to push the Einstein scale all the way to the string scale in this case, or the Kaluza-Klein scale there, of course, the full tower is important. But to see that the leading Einstein scale is cancelled and the subleading sets in, you need the first two elements in the tower, of course. And of course, by induction, you can suspect that this may happen further.
Okay, great.
To see the first cancellation of each, you need the first two levels in the tower. Of course, to see the whole cancellation all the way to the string scale, you need to add them all, which in this particular case, of course, I don't think it's doable.
All right.
But Elias, in the Kaluza-Klein case, they put a very large box, I mean, a very small mass. Why here, the mass square is 1 over alpha prime. I mean, the Einstein scale is the same as from the beginning.
No, I don't think so, in fact. The Einstein scale involves also the string coupling, or if you wish, the Planck scale, and you can make it smaller. In fact, if you are at weak coupling, it is smaller.
Is there any assumption on alpha prime in this setup, Elias? So like small alpha prime or so thought of?
Small alpha prime doesn't mean anything. You have to compare it with something. Usually you compare it to M Planck, and it has to be, 1 over alpha prime has to be much smaller than M Planck. That's the usual assumption, so that you are at weak coupling.
Mm-hmm. Okay.
May I say something? I think the case of Kaluza-Klein is different because in the limit, once you consider the tower of Kaluza-Klein stands, we just go to higher dimensions. So you have same as a graviton in higher dimensions. While here is different because the regularization of the theory is not only due to spin 2s, there are higher spins in this string theory. Moreover, in this calculation, go back to Guillaume comment. I mean, open strings have also some patterns. So whatever the theory is, should admit a non-abelian structure, some pattern structure. So it's difficult to imagine that this is part of, that it's a Riemann tensor, if you want. While
I didn't say, Nadia, that this is a Riemann tensor, but whatever it is.
About you, I said that, I mean, the first comment was about the Kaluza-Klein. The second was about the open string part of, I mean, of spin 2, which is part of the open string sector. Because the open string sector has by default gauge group.
Right.
Right.
Okay, so it's difficult to imagine that you have a gauge group with a Riemann tensor.
I understand.
The closed string part that you mentioned, yeah, that's different. This may have something. This may give something on trivia.
Exactly, yeah. So I'm inclined to think that this might work, although still it's intuitive to say that still. I wanted to say again that I understand what you're saying, both Ignatius and Elias, and Guillaume started, I think, in regard to the coefficients. I mean, in regard to the gauge group disturbing, so to speak, the Riemann-Ricci structure. I understand that. But here we're talking about the same order again. So I don't know if you could have foreseen this. I couldn't have foreseen this. I don't know even if the Ricci, you can, in some sense, if you don't do the calculation, you don't know what will come out. Gross and Sloan had to do the calculation to find that it's the Ricci.
Chrysoula, here you can ask a very simple question. You have a quadratic term and it's proportional to trace the ATA. The question is, these various terms, when you put the Chan-Paton factor, which traces of the generators do they include? I think this is important to see how this structure develops.
Yes, yes. So in the paper, we even have it here. It becomes
it's written,
something
right?
like this.
Okay, very good.
Yes, yes, yes,
right.
Absolutely. Right.
Let me just cut for a second. We can continue the discussion informally, but let me check if there are other questions before I stop to record the talk.
Oh.
If not, I propose we thank Chrysoula again. And
thank you, Chrysoula.
And now